All right, welcome. We're going to be going over focusing on how to balance chemical equations, but we're basically going to review right now is why we do it. Again, a chemical reaction is just an equation that basically provides us a recipe. It tells us our reactants in our products, so what goes in and then what's produced at the end. Substances being reacted are called our reactants. The ones that are being formed we refer to as the products. Reactants are always on the left, products are always on the right. We also can show our phases. We can represent the number of moles, which we'll focus on next unit. And we can also show energy that's lost or gained. All reactions must conserve mass, charge, and energy. This simply means that the total mass, energy content, and electric charge of the reactants must be equal to those of the products. They have to be equal to each other on both sides of the arrow. Now, for us to show a conservation of mass, we're going to use coefficients. And we can only change the coefficients. We cannot touch any of the subscripts. And remember, the coefficients are these blue numbers out in front. The 2's, the subscripts, we cannot touch at any point while we are balancing. This is a strategy. Some students refer to it as the minnow strategy. Some refer to it as the chemistry strategy. In a Tarzan voice, whichever works for you is fine. This kind of gives you an order or kind of like a template to follow when we're going to be balancing these. You start off with metals. You then balance out any polyatomic ions. If anything's left to be balanced, you work with the nonmetals before moving on to oxygen and hydrogen. So we're going to go through a couple of these examples. The big thing is that I'm going to show you the strategy where we're going to be tallying and writing stuff below it. It's just a way for many students to organize their information. So the first step is I'm going to list each of the elements. So I have C, H, and O. I'm going to keep the same order on the right. Okay, I'm going to make sure that I have nothing in parentheses, so I don't need to worry about counting at this one. I'll point some things out in a further example. I have 1 carbon on the left. I have 4 on hydrogen on the left, and I have 2 oxygen. And then on the right, I have 1 carbon, I have 2 oxygen, oh, I'm sorry, I'm going to go back to that one. I have 2 here, okay, and I have 1 here. I'm going to add them together. We never want to write them separately because that will definitely throw you off. So I have 3 total oxygen, and then I just have 2 hydrogen. Okay, so let's go ahead and balance them. My carbons are already at the moment balanced, so I can leave those alone. So then we're going to work with our oxygen. Now, normally that's the next thing on our list, but since it's in 2 spots, I'm going to hold off and see by balancing the hydrogens if that will balance out my oxygens. So if I already have 4 on the left, I want to think about what can I put in front of this H2 that will make me have a total of 4. Well, 2 times 2 can give me a total of 4. So that correctly balances that part. I now, though, have to update anything else that's attached to that compound. So this now means I have 2 oxygen. So 2 plus 2 now shows that I have 4 oxygen. So carbons, hydrogens, all set. I just need to finish off on the left with oxygens. So I'm going to place a 2 out in front because 2 times 2 is going to get me 4. So now carbons, hydrogens, oxygens are all set. You can go ahead and place 1s in front of the methane, CH4, and the carbon dioxide, CO2. All right, for this next one again, go ahead, write down Al, Br, K, and then write down the same order on the other side, Al, Br, and K for potassium. Go ahead and count them. We only have 1 Al, we have 3 bromine, and 1 potassium. On the other side, we just have 1 of each. So this one's pretty straightforward because the aluminums right now are balanced, potassiums are balanced, so I can move on to my bromine nonmetal. This one, again, what times 1 will get me up to the 3 that I need to balance out the other side. That would be a 3. That's going to change my bromine to 3, but also changes potassium. You can't forget about that change. So 3 potassium I now have on the right. So aluminum, bromines match. Potassium, though, I need to now make a 3 on the left. 3 times 1 is going to give me a total of 3. So now everything's all set. Those all balance. I can go ahead and just place 1s in front of the remaining compounds. I have conserved mass, so this one is all set. All right, this one, if you can just make sure before we start this that you change this formula. You needed to add a 2 in after Fe and then make sure the CO3 is in parentheses with a 3 after it. Now this one's going to be different because we have a polyatomic ion. Because CO3 is written exactly the same on both sides, I'm going to keep it and count it as 1 instead of breaking up carbon and oxygen, which makes this much tougher. So go ahead, I'm going to write FeCl Na, and then CO3 as a group. And then same order, FeCl, Na, and CO3. So go ahead and count them. Iron, I just have 1. Chlorine, I have 3, 2 sodium, and in this case, 1 CO3. Because remember, this 3 is a part of the CO3. It's not telling you that you have 3 of them. On the right, I have 2 iron. I have 3 CO3s. We're not going to multiply or add these together at all. We're only looking at this 3. I have 1 sodium and 1 chlorine. So I'm going to start off with my metals. My iron and sodium right now are incorrect. So I'm going to work with iron first. We have 1 on the left, 2 on the right. So I'm going to focus on just the left-hand side. And I'm going to make sure that I get 2 iron on my left. 2 times 1 means I now have 2 iron. This also affects chlorine. 2 times 3 means I now have 6 chlorine. All right, if we look at sodium, we could go ahead and balance this out first. I'm going to write it a little bit smaller because I know we're going to have to update it, and I don't have a way of erasing this. So I'm going to place a 2 out in front of NaCl. 2 then would mean I have 2 there, and now I have 2 chlorine. All right, now I can look at my, I could look at the polyatomic ion. So if we change that, we have 1 CO3 on the left, 3 on the right. So I want to place a 3 in front of Na2CO3. That means then I now have 3 CO3s, which is great. That's what I wanted, 3 times 1. But I've also changed the sodium. So 3 times 2 now means I have 6 sodium. So now if we look, iron, the CO3 polyatomic ion is all set, but Na and Cl are incorrect. But we can see that we have 6 chlorine and 6 Nas. So this is an easy fix. You can just erase the 2. And then I'm going to place a 6 out in front of NaCl. That happens a lot. Sometimes you have to update the numbers that you started with. So I can now make these each 6, and now everything balances. I can now go ahead and place 1s in the rest of the coefficient spots, and this one has been successfully balanced. All right, the last one of these that I'm going to specifically work with you on. Again, go ahead. Mn is going to be equal to 2 on the left. CO3 is back as a pack on both sides, so I'm going to use CO3 as a group. So let me just go ahead and make parentheses around that. So remember on the right, I have 3 CO3s, Mg, I just have 1, and NO3, okay, I have 2. And now I'm going to go and copy down the same list on my right. So Mn, CO3, Mg, and NO3. Okay, Mn I just have 1, NO3 I have 3 of them. I have 1 Mg and only 1 CO3 because remember the CO3, the 3 is a part of that group. All right, so let's look at our metals. Mgs are okay, but Mns are not. So I'm going to go ahead and place a 2 out in front of MnNO3, 3, which changes Mn to 2. However, NO3 I've now done 2 times 3, which now means I have 6. Okay, so Mn, Mgs are balanced, however, our polyatomic ions are not. Oops, and I gotta just make sure I have another tally to have a total of 6. So I'm gonna balance out the NO3s at the moment. So I have 6 NO3s on my right and only 2 on my left. So again, I'm thinking of what can I put here that times 2 will give me and get me up to 6. So that would be a 3. 3 times 2 means I now have 6 on my left, which is wonderful, but I've also affected Mg, so now I also have 3 Mgs, because again, coefficient of 1 there, 3 times 1. All right, and now I just got to go back to fixing Mg, because that's my metal. It looks like I'm going to have to place a 3 in front of the MgCO3 in order to get this up to the left-hand side. And then I've also affected the CO3. So 3 times 1 is going to then mean that I have 3 CO3s. Everything now matches. I have conserved mass correctly, and I can place a 1 in the remaining coefficient spots. Chemical reactions and learning how to classify them. Our first type is a synthesis reaction. This is when 2 or more reactants combine into one product. So the big idea is you're going to be looking for, when you classify a synthesis reaction, is that you have many pieces on the reactant side and only one piece on the product side, because all of your reactants are going to come together to form one product. Now, a representation of this in real life would be any couple that starts dating. That is representing a synthesis reaction. All right, the second type of reaction is a decomposition reaction. This basically looks the opposite of a synthesis reaction. This is where one reactant breaks down into two or more products. So here we have one, again, reactant, in this case water, and it's going to break apart into many pieces. So you're only looking for one piece on the left in terms of your reactants, and then it should be breaking apart into two or more pieces on the right, and that is, again, a decomposition reaction. And again, this can be represented in real life by any couple that breaks up, and that, again, is symbolic of a decomposition reaction. All right, single replacement. One element replaces another less reactive element in a compound. So if you look down at the bottom, you're always going to see a single element and then a compound as your two reactants. And what happens is that single element is basically going to come in and kick out the positive metal ion and take its place. So as you can see, iron and copper have switched places from the reactant side to the product side, and this is called a single replacement. Again, you're going to be looking for an element by itself and a compound, and you're going to be seeing that the two metal elements are switching places. So this is similar to the graphic that you see on your screen. Mary was basically with Frank, and then she dumped him and started dating Joe. And while it's great for Joe, now poor Frank is by himself. So again, representing a single replacement reaction. The fourth reaction is a double replacement reaction. This is when two elements exchange places between two separate compounds. Now, this looks different than a single replacement reaction because, remember, that kind had an element with a compound on your reactant side on the left. Now we have two compounds. And what you're going to see is that the positive metallic ions in front are going to be switching places. So Ag was originally with NO3, now it's with Cl. Potassium was with Cl, and now it's with NO3. So this is a double replacement reaction. Those ions are switching places. And this would be like dance partners. As you can see with the bottom here, A was originally with B, and now it is switched with C, so that is dancing with the person in the shirt with a letter D. All right, and the last one that we're going to be covering today is combustion, and this is when a hydrocarbon is going to be burning in the presence of oxygen, carbon dioxide, and water are produced. So a hydrocarbon is made up of carbons and hydrogens that's going to be combining with oxygen gas, O2, and it's going to always produce CO2, carbon dioxide, and water. All right, that's all you need from this concept, and we'll be classifying more in class